Hi everyone, welcome this new topic, network layer characteristics. In the first point, the network layer. The network layer or OSI layer 3 provides service to allow end devices to exchange data across networks. As shown in the figure, IP version 4 and IP version 6 are the principal network layer communication protocols. Other network layer protocols include routing protocols such as Open Shortest Path First (OSPF) and messaging protocol such as Internet Control Message Protocol (ICMP). And this is the model OSI is the layer 3 network layer with IPv4 and IPv6. To accomplish end-to-end communications across network boundaries, network layer protocols perform four basic operations: addressing end devices. End devices must be configured with a unique IP address for identification on the network. Encapsulation: the network layer encapsulates the protocol data unit (PDU) from the transport layer into a packet. The encapsulation process adds IP header information, such as the IP address of the source (sending) and destination (receiving) host. The encapsulation process is performed by the source of the IP packet. The next step is routing. The network layer provides service to direct the packets to a destination host on another network. To travel to other networks, the packet must be processed by a router. The role of the router is to select the best path and direct packets toward the destination host in a process known as routing. A packet may cross many routers before reaching the destination host. Each router a packet crosses to reach the destination host is called a hop. The encapsulation: when the packet arrives at the network layer of the destination host, the host checks the IP header of the packet. If the destination IP address within the header matches its own IP address, the IP header is removed from the packet. After the packet is encapsulated by the network layer, the resulting layer 4 PDU protocol data unit is passed up to the appropriate service at the transport layer. The encapsulation process is performed by the destination host of the IP packet. Unlike the transport layer, OSI Layer 4, which manages the data transport between the process running on each host, network layer communication protocol (IPv4 and IPv6) specify the packet structure and processing used to carry the data from one host to another host. Operating without regard to data carried in each packet allows the network layer to carry packets for multiple types of communication between the multiple hosts. And we have a video. Press play in the figure to view an animation that demonstrates the exchange of data. Okay, data from host with IP 192.178.32.11, layer 4, transport layer, layer 3, network layer, layer 2, and layer 1. Okay. In these steps, they encapsulate the information of the data and receive the host the information. And IP encapsulation. IP encapsulate the transport layer, the layer just above the network layer, segment or other data by add an IP header. The IP header is used to deliver the packet to the destination host. The figure illustrates how the transport layer PDU protocol data unit is encapsulated by the network layer PDU to create a IP packet. And transport layer encapsulation segment header. more data is transport layer PDU, and network layer encapsulation is IP header, more data, network layer PDU, IP packet. The process of encapsulating data layer by layer enables the service at the difference layer to develop and scale without affecting the other layers. This means the transport layer segments can be readily packaged by IPv4 or IPv6 or by any new protocol that might be developed in the future. The IP header is examined by the layer 3 device, router, and layer 3 switches as it travels across a network to its destination. It's important to note that the IP header information remains the same from the time the packet leaves the source host until it arrives at the destination host, except when translated by the device performing network addressing translation NAT for IPv4. Note: NAT is discussed in later modules. Routers implement routing protocols to route packets between networks. The routing performed by these intermediary devices examines the network layer addressing in the packet header. In all cases, the data portion of the packet, that is the encapsulated transport layer PDU or other data, remains unchanged during the network layer process. Characteristics of IP: IP was designed as a protocol with low overhead. It provides only the functions that are necessary to deliver a packet from a source to a destination over an interconnected system of networks. The protocol was not designed to track and message the flow of packets. These functions, if required, are performed by other protocols at the other layers, primarily TCP at layer 4. These are the basic characteristics of IP. Connectionless: there is no connection with the destination established before sending data packets. Best effort: IP is inherently unreliable because packet delivery is not guaranteed. And media independent: operation is independent of the medium, copper, fiber optic, or wireless carrying the data. Connectionless: IP is connectionless, meaning that no dedicated end-to-end connection is created by IP before data is sent. Connectionless communication is conceptual, similar to sending a letter to someone without notifying the recipient in advance. The figure summarizes this key point. Connection analogy: we have the letter is sent in the mailbox, and the truck is sent the letter, and the letter arrived to the house of someone. And connectionless data communications work on the same simple principle. As shown in the figure, IP require no initial exchange of control information to establish end-to-end communication before packets are forwarded. Connection network: IP header segment, a packet is sent across the routers, and IP header segment arrive in the destination host. Best effort: IP also does not require additional fields in the header to maintain an established connection. This process greatly reduces the overhead of IP. However, with no pre-established end-to-end connection, senders are unaware whether destination devices are present and functional when sending packets, nor are they aware if the destination received the packet, or if the destination device is able to access and read the packet. The IP protocol does not guarantee that all packets that are delivered are, in fact, received. The figure illustrates the unreliable or best effort delivery characteristics of the IP protocol. Packets are routed through the network quickly, and some packets may be lost en route. As an unreliable network layer protocol, IP does not guarantee that all sent packets will be received. Other protocols manage the process of tracking packets and ensure their delivery. Media independent. Unreliable means that IP does not have the capability to manage and recover from undelivered or corrupt packets. This is because while IP packets are sent with information about the location of delivery, they do not contain information that can be processed to inform the sender whether delivery was successful. Packets may arrive at the destination corrupted, out of sequence, or not at all. IP provides no capability for packets retransmission if errors occur. If out-of-order packets are delivered or packets are missing, then application using the data or upper layer service must resolve these issues. This allows IP to function very efficiently. In the TCP/IP protocol suite, reliability is the role of the TCP protocol at the transport layer. IP operates independently of the media that carry the data at lower layer of the protocol stack. As shown in the figure, IP packet can be communicated as electronic signals over copper cable, as optical signals over fiber, fiber optics, or wirelessly and radio signals. Okay, packets across or is sent across the router, copper serial, optical fiber, and copper Ethernet, and finish with wireless. And IP packets can travel over different media. The OSI data link layer is responsible for talking an IP packet and preparing it for transmission over the communication medium. This means that the delivery of the IP packet is not limited to any particular medium. There is, however, one major characteristic of the media that the network layer considers: the maximum size of the PDU that each medium can transport. This characteristic is referred to as the maximum transmission unit (MTU), part of the control communication between the data link layer and the network layer is the establishment of the maximum size of the packet. The data link layer passes the MTU value up to the network layer. The network layer then determines how large packets can be. In some cases, an intermediate device, usually a router, must split up an IPv4 packet when forwarding it from one medium to another medium with a smaller MTU. This process is called fragmenting the packet, or fragmentation. Fragmentation causes latency. IPv6 packets cannot be fragmented by the router. And finish with check your understanding IP characteristics, which oscillator sends segments to be encapsulated in an IPv4 and IPv6 packet that is transport layer, which oscillator sends segments to be encapsulated in an IPv4 and IPv6 is the above layer over network layer is transport layer. In question 2, which layer is responsible for talking an IP packet and preparing it for transmission over the communications medium, that is data link layer. Question 3, what is the term for splitting up an IP packet when forwarding it from one medium to another medium with a smaller MTU? This is fragmentation. And which delivery method does not guarantee that the packet will be delivered full without errors? This is best effort. And IPv4 packets header. IPv4 is one of the primary network layer communications protocols. The IPv4 packet header is used to ensure that this packet is delivered to its next stop on the way to its destination and device. An IPv4 packet header consists of fields containing important information about the packet. These fields contain binary numbers which are examined by the layer 3 process. IPv4 packet header fields. The binary values of each field identify various settings of the IP packet. Protocol header diagrams, which are read left to right and top down, provide a visual to refer when discussing protocols field. The IP protocol header diagram is in the figure identify the fields of an IPv4 packet. Fields in the IPv4 packet header. The first point is version, internet header length, DS, total length, identification, flag, fragments offset, time to live, protocol, header check, source IP address, and destination IP address. And this point is the data. Significance fields in the IPv4 header include the following. The first is version, contain 4-bit binary values set to 0100 that identify this as an IPv4 packet. Okay, this binary value identify this as an IPv4 packet. And service of diffserv, formerly called the type of service TOS field. The DS field is an 8-bit field used to determine the priority of each packet. The six most significant bits of the diffserv field are the differentiate service code point DSCP. Okay, this is DSCP. Bits and the last two bits are the explicit congestion notification ACN bits. Time to live TTL. TTL contain an 8 bits binary value that is used to limit the lifetimes of packets. The source device of the IPv4 packets sets the initial TTL value. It is decreased by 1 each time the packet is processed by a router. If the TTL field decrements to 0, the router discards the packet and sends an Internet Control Message Protocol (ICMP) time exit message to the source IP address, because the router decrements the TTL of each packet. The router must also recalculate the header checksum protocol. This field is used to identify the next level protocol. This A binary value indicates the data payload type that the packet is carrying, which enable the network layer to pass the data to appropriate upper layer protocol. Common values include ICMP, TCP, and UDP. Okay, ICMP is 1, TCP 6, and UDP is 16. 17. Header checksum. This is used to detect corruption in the IPv4 header. Source IPv4 address. This contains 32-bit binary values that represent the source IPv4 address of the packet. The source IPv4 address is always a unicast address. And destination IPv4 address. This contains 32 binary values that represent the destination IPv4 address of the packet. The destination IPv4 address is unicast, multicast, or broadcast address. The two most commonly referenced fields are the source and destination IP address. These fields identify where the packet is coming from and where it's going. Typically, this address does not change while traveling from the source to the destination. The Internet header length IHL, total length, and header checksum fields are used to identify and validate the packet. Other fields are used to reorder and fragmented packets. The IPv4 packet use identification, flags, and fragment offset fields to keep track of the fragments. A router may have to fragment an IPv4 packet when forwarding it from one medium to another with a smaller MTU. The options and padding fields are rarely used and beyond the scope of this module. Sample of IPv4 headers in Wireshark. Wireshark is a tool for sniper packets across the network and check your understanding IPv4 packets. What are the two most commonly referenced fields in the IPv4 packet header that indicate where the packet is coming from and where it is going? Choice 2. Choose 2 destination IP address and source IP address. And which statement is correct about IPv4 packet header fields? The source and destination IPv4 address remain the same while traveling from source to destination. And which fields is used to detect corruption in the IPv4 header checksum. Which field include common values such as ICMP, TCP, and UDP. This is the protocol. The last topic is IPv6 packet, limitation of IPv4. IPv4 is still in use today. This topic is about IPv6, which will eventually replace IPv4. To better understanding why you need to know the IPv6 protocol, it helps to know the limitations of IPv4 and the advantage of IPv6. Through the years, additional protocols and processes have been developed to address new challenges. However, even the challenge, IPv4 still has three major issues. IPv4 address depletion. IPv4 has a limited number of unique public addresses available. Although there are approximately 4 billion IPv4 addresses, the increasing number of new IP-enabled devices, always-on connection, and the potential growth of less developed regions have increased the need for more addresses. This is depletion. The next point is lack of end-to-end connectivity. Network Address Translation (NAT) is a technology commonly implemented within IPv4 networks. NAT provides a way for multiple devices to share a single public IPv4 address. However, because the public IPv4 address is shared, the IPv4 address of an Internet network host is hidden. This can be problematic for technologies that require end-to-end connectivity and increased network complexity. While NAT has extended the lifespan of the IPv4, it was only meant as a transition mechanism to IPv6. NAT its various implementation creates additional complexity in the network, creating latency and making troubleshooting more difficult. IPv6 Overview. In the early 90s, the Internet Engineers Task Force (IATF) grew concerned about the issues with IPv4 and began to look for a replacement. This activity led to the development of the IP version 6. IP version 6 overcomes the limitation of the IPv4 and is a powerful enhancement with features that better suit current and foreseeable network demands. Improvements Improvements that IPv6 provide include the following: increase address space, increase address space. IPv6 addresses are based on 128-bit hierarchical addressing as opposed to IPv4 with 32 bits. Improved packets handling. The IPv6 header has been simplified with few fields and eliminates the need for NAT, with such a large number of public IPv6 addresses. NAT between a private IPv4 address and public IPv4 is not needed. This avoids some of the NAT include problems experienced by applications that require end-to-end communication. The 32-bit IPv4 address space provides approximately for this amount unique address. IPv6 address space provides this other amount of addresses, or 340 undecillion addresses. This is roughly equivalent to every grain of sand on Earth. The figure provides a visual to compare the IPv4 and IPv6 address space. Okay, on the zillion, there are 4 billion IPv4 addresses. There are 340 on the zillion IPv6 address. IPv4 packet header fields in the IPv6 packet header. One of the major design improvements of the IPv6 over IPv4 is the simplified IPv6 header. For example, the IPv4 header consists of a variable length header of 20 octets, up to 60 bytes if the options field is used, and 12 basic header fields, not including the options fields and padding field. For IPv6, some fields have remained the same, some fields have changed names and positions, and some IPv4 fields are no long required as highlighted in the figure. IPv4 packet header version IHL, type of service, total length, identification, flags, fragment offset, time to life, protocol, header checksum, and options padding. The figures show IPv4 packet header fields that were kept, moved, changed, as well as those that were not kept in the IPv6 packet header. In contrast, the simplified IPv6 header shown in the next figure consists of a fixed-length header of 40 octets, large due to the length of the source and destination IPv6 address. The IPv6 simplified header allows for more efficient processing of IPv6 header. IPv6 packet header version, traffic class, label, payload length, next header, hop limit, and source and destination addresses. Fields no longer required in IPv6. Name and position change in IPv6 and fields name kept from IPv4 and IPv6. The figures show the IPv4 packet header fields that were kept or moved along with the new IPv6 packet header field. IPv6 packet header. The IP protocol header diagrams in the figure identify the fields of an IPv6 packet. Fields in the IPv6 packet header. And the fields in the IPv6 packet header include the following: version, traffic class. This 8-bit field is equivalent to the IPv4. Okay, flow label. This 20-bit field suggests that all packets with the same flow label receive the same type of handling by routers. Okay, flow label. Payload length. This 16-bit field indicates the length of the data portion of payload. Okay, this does not include the length of the IPv6 header, which is a fixed 40 bits header. Next header, hop. Okay, and check your understanding. Which three options are major issues associated with IPv4? Choice 3. Duplication, increased network complexity, and internet routing table expansions, and always on connection. Okay, okay, lack of end-to-end connectivity. Okay. Which two options are improvements provided by IPv6 as compared to IPv4? Headers support additional fields for complex packets, increase the IPv4 address space, support class. Okay, which two options are improvements provided by IPv6 as compared to IPv4? Support class, header supports additional. Okay, show me the answers. Increase the IPv4 address space, the IP address space, and use a simple header to provide improved packet handling. Okay, okay. Which is true of the IPv6 header? Okay, okay, choice two. Okay. And which is true of the IPv6 packet header? The hop limit field replaced the IP4 time to life field. The source and destination IPv6 header changed, no. The time to life field replaced, no. The version field identify the next header. That's right. Several fields in the IPv6 header replace fields in the IP4 header. For example, the hop limit field replaced the IPv4 header time to life field. Hop. Okay. And network layer summary. Okay, this is for the next. See you in the next one. Bye.